And the recording is live. Okay. Uh, Before jumping into today's topic, I just want to give you guys an overview of what the next couple of lectures are going to look like. So, of course, last Monday we had the first exam, module exam 1, and then on Wednesday we jumped into our next topic called the mole concept. Now, I want you to notice that for the next 3 lectures, that is today, Wednesday, and next Monday, we're actually going to be spending a lot of time on one single big topic called reactions. All right. Now, this topic is probably the single biggest topic we will encounter in Chem 1A. It's a topic that you will continually find yourself coming back to, even in Chem 1B, organic chemistry, and even further chemistry-based courses. All right. So that is all to say that we're not going to finish it all in one session. You're not going to understand it all in one session. But the point is that we will continually build on it over the next few days. All right. Please note, of course, that we do have a wet lab today, experiment 2, right after lecture. But this Wednesday, we have a dry lab focused on this topic. So the point of lecture, as always, is to get all of that content out and written in your notes. And then there will be an opportunity on Wednesday, during Wednesday's lab, that we'll have some practice sessions, a focused practice session on this exact topic. All right. My goal is that by next Monday, the 22nd, we'll have covered all of reactions and content and have an extra day of lecture just to devote to practicing reactions and predicting reactions. In front of you, you all should have a single handout, both pages back and front. I want to make one thing clear. Now, this document is going to be available on Canvas once the class is over. There are 2 sides to this page. I want to make something clear. This side with the table that says if a compound contains then it is except when bonded to. This is a table you will be getting as part of your exam booklet, just like the periodic table. The next page, you will not get this part of the handout. So I want you all to make a note of that on your individual copies. The first table that just says if a compound contains then it is except when bonded to. This is a table you will get as part of your exam booklet. It's a reference sheet. It's going to be part of the exam itself. So you don't need to memorize this table, but you do need to understand it. And then the second page is just a general handout that summarizes all of the reactions that we're going to go over in class. So the second page is just a general summary of our content. It is not something I expect you to memorize, just rather understand and just organize your notes and information. You will not be getting this table as part of the exam booklet. Okay, it's something that you need to study and understand. Does anyone have any questions on this or about lecture before we begin? Yes. Any other questions? Okay. Great. Oh, sorry, Joe. What's up? Yes. Yes. Great. And that's something we'll talk a little bit about when we get to this part of the lecture about this table. I just wanted to make that part clear first. All right. Today, our big topic is called reactions. We're going to go over a couple of things about reactions over the next couple of days. Just wanted you all to understand. First and foremost, we're going to understand what exactly is called balancing reactions. We're going to go over and try to understand something known as state symbols. And state symbols go hand in hand with what is known as solubility rules. We're going to cover different types of reactions, herein called reaction archetypes. Under reaction archetypes, we're going to cover how to predict the products of a reaction and write different forms of that same reaction. Once we complete reactions, we're going to introduce mathematical calculations to them, which I'll talk about once we get closer. But for the next couple lectures, we're actually going pretty light on math or the calculator stuff. It's very bird's eye view, very content heavy. So one of the first things I want to talk about is a reaction, specifically balancing chemical reactions. Now, in theory, we all understand the basic idea of a chemical reaction. If you've ever cooked or baked, then you understand the idea of mixing things together in a specific amount, right? If you've ever even made lemonade, you understand the basic idea of a reaction. We're putting things together to make more things. Now, while we'll go into a much more formal definition of what a reaction is and the different types, the first thing we wanted to talk about was something known as balancing chemical reactions. So here is a generic reaction. Where we have the reaction between the compound copper sulfide and the other compound hydrogen chloride. And that results in the following products: copper chloride and dihydrogen sulfide. Now, if you recall, I mentioned that nomenclature was one of the more weaker topics on the first exam. This is a good example of why it becomes so important to have a steady understanding of how to name. Because as you notice, when I named all these compounds, I just said their names: copper sulfide, hydrogen chloride, copper chloride, and hydrogen dihydrogen sulfide. Right. So you're no longer going to get explicit questions on an exam that say, what is the name, what is the formula, but you'll get things like this where you should be able to read the reaction. On the left-hand side, we call this the reactant side. You'll also hear sometimes we'll just refer to it as the left side of the reaction. Similarly, on the right-hand side, we have what are known as the products. And again, sometimes this will be loosely referred to as the right side of the equation. The most important thing I want you to be able to understand here or recognize is this goes back to one of our Dalton's law atomic theories, which is that matter can neither be created nor destroyed, but merely transformed. In other words, the amount of each atoms must remain the same. Take, for example, Cu right here, copper. Well, we can see as written, there is only one copper on the left. How do we know that? Well, if there were two of them, we'd write two. Or if there were three of them, we'd write three. Clearly, with nothing written, we're allowed to assume that there's one of them. There is one copper on the left, and as we can see as of right now, there is one copper on the right. This is a situation where the amount of coppers has been conserved, so everything's fine and dandy with regards to copper. We can apply the same logic to sulfur. There is only one sulfur on the left. There is only one sulfur on the right. But as we further investigate, if we look at, for example, hydrogen, we should immediately notice that there's actually only one hydrogen on the left, but there are two hydrogens on the right. This is our first indicator that this reaction is currently unbalanced and therefore needs to be balanced. All right, if we keep going, we look at Cl, same thing again. There's only one chlorine on the left, but we see there are two chlorines on the right. Of course, this is an all or nothing thing. If one part of the reaction is unbalanced, then the entire thing is unbalanced. But we have, of course, proven that in the context of HCl, it is not balanced at all. So we need to balance that. What do I mean by balance? Well, we first just take stock of how much of each element or atom we have. Like I've already said, we have one copper, we have one sulfur on the left. Currently, we have one hydrogen on the left. Currently, we have one chlorine on the left. But on the right-hand side, although the number of coppers and sulfur stays the same, both 1. We only have we have 2 hydrogens and 2 chlorines. What we'll do now is we'll go 1 atom at a time, doesn't matter the order, 1 atom at a time, and modify the reaction so that it is balanced. Now, like I said, it doesn't matter the order that you pick. We immediately notice that the hydrogen and chlorine are the problematic ones. So we can start with them. But as you're going through these questions, traditionally we just work from left to right. We've already gone over copper. Copper is balanced as is. There's 1 on the left, 1 on the right. So I just put a little check mark. There is 1 sulfur on the left, 1 sulfur on the right. There's a check mark right there. Okay, now we see hydrogen. There's only 1 hydrogen on the left, and there's 2 hydrogens on the right. This is clearly a situation that's unbalanced. So to balance it, we are going to put a 2 in front of the HCl. Now notice that even though the hydrogen on the right has their 2 as a subscript, meaning smaller, that bottom right corner, the one we are writing is carefully and more purposefully bigger and in front. Here is the distinction. The subscript simply refers to the amount of hydrogens in that molecule. That subscript comes from the crisscross method that we've grown accustomed to. Hydrogen is in group 1, so it's +1. Sulfur is in group 16, so it's 2-. The crisscross result of these 2 is, of course, H2S. So the subscript 2, or rather all subscript numbers, are a reflection of the crisscross. The big number in front is not a result of crisscross, but rather a result of balancing. So you will often hear me refer to different numbers in the equation. I will say something such as subscript 2, meaning the small 2 written after the letter, and then the balancing 2. The balancing 2, which is written in front of the compound, making it very clear this is not crisscross, but rather an attempt to balance the 2. Now, in doing so, we have, in fact, balanced our hydrogens. Now we can clearly see that there are 2 hydrogens on the left. And now by putting the 2 in front, we can say there are 2 hydrogens on the left. That's our fix. Now let's take a look at the chlorine. Now, technically speaking, solely based on the circle, there is only 1 chlorine. But remember what we just did for the hydrogen. We put a 2 in front of it. And if this 2 is about balancing, what this is literally saying is that there are 2 hydrogen chlorides. We expected and wanted there to be 2 hydrogens. That's, of course, what the point was. But now that we've added the 2, we're also implying there are 2 chlorines. So without purposefully trying to do anything, we have now changed the number of chlorines present to 2. Lo and behold, though, magically, quite literally serendipitously, now the chlorine is balanced. So I want you to understand that very simple principle. As you attempt to balance a reaction, most likely by the time you finish, everything will be balanced for you automatically. In this case right here, we first balanced the hydrogen, and we serendipitously also balanced the chlorines. This reaction, now as written, is completely balanced. There is an equal amount of coppers, an equal amount of sulfurs, an equal amount of hydrogens, an equal amount of chlorines. I see your hand, Elaine. I'll be right there in a second. But the really, really important part I want you to remember, these small subscript numbers are a result of the crisscross nature. This small subscript number tells us there are 2 hydrogens in this molecule, but there is only 1 sulfur. The big number in front tells us there's two of everything. In this case, there are two hydrogens and two chlorines. Elena, what was your question? So that just comes down to laziness in teaching. When I'm speaking out loud, I'd rather just say copper sulfide, but when writing, I'm going to write copper 2 sulfide. Right. Elena, I see your hand, Sarah. Elena's pointed something very important out that I do want to spend a little second on. Hopefully, we all recognize copper as a transition metal. Whoops, sorry. As a transition metal. We've talked about how we cannot just look at the periodic table and identify transition metals charge. We have to have some information with us to give us the hint. Here we have sulfur, which is in group 16, and we know that group 16 is 2 minus. Since we know there is only one of each atom, there's one copper, one sulfur, this is what tells us directly that the copper must be 2 plus. As Elena pointed out, technically the correct name for this molecule is copper 2 sulfide. And when writing, I would include the Roman numerals. But when just speaking to you casually, especially in a lecture delivery, I'm just going to say copper sulfide because you should have enough information to figure out the charge. The same thing can be said for the product side. Again, we have here copper, transition metal. We can't know for sure what its charge is, so we look at what else we have. We have chlorine. Right here, we know chlorine is in group 17. That means that there is only a -1 of the chlorine. That makes sense. There's only one copper, so the crisscross makes sense. That's what's shot down. Of course, that's what tells us that the 2 is a result of the copper, hence 2 plus. We talked about that being reverse crisscross. So in both cases, there is enough information present that you are able to reasonably come up with the idea that copper is 2 plus. Sarah, what was your question? Something else more complicated is, yeah. So yeah, that's a really, really good question. That's what we're going to do an example of right now. But I want to be sure, do we all understand this example right in front of us? Okay. Now we're going to do another one. H3PO4 plus Na2SO4 gives us Na3PO4 plus H2SO4. Does this one work logically? Let me just make sure in my head. So actually this one does not work. So let's, instead of using sulfate on the sulfur, let's use NaCl, and that leads us to HCl. Yes. All right, remember, as of this moment, you don't know how I got the products, right? So we're only focusing on balancing right now. So over the course of the semester, you'll be able to balance these things in your head. But in the beginning, as you're practicing, I do recommend purposefully writing it out like this. On the left-hand side, there are 3 hydrogens. On the left-hand side, there is 1 PO4, 1 sodium, 1 chlorine. On the right-hand side, there are 3 sodiums. Let me make sure that they're roughly the same order. Hydrogen, PO4, Na, and Cl. There is 1 hydrogen, 1 PO4, 3 sodiums, and currently 1 chlorine. So in the beginning, I do recommend you take the effort to write them out like this, that way you're more clearly able to see how much of each there are. something I want to immediately point out so you notice is the polyatomics. The polyatomics are regarded as one ion, meaning I would not break this up into saying one phosphorus and 4 oxygens. I would simply say there is one PO4. That's a very important principle I want you to make clear. Polyatomic ions, which you were told to memorize, you should be able to recognize them as a singular unit. Okay. Now, we're going to arbitrarily go, as I mentioned, we like to go in order from left to right, starting off with hydrogen. There are 3 hydrogens on the left. Currently, there's only 1 hydrogen on the right. So this is immediately unbalanced. So let's balance it. What number do we need to put to balance this out? Well, hopefully we all have the same logic of 3, because there's 3 on the left, there's 1 on the right. But the question is, do we put the 3 on the left or do we put the 3 on the right? Let me be a little bit more specific. Should I put the big 3 here or should I put the big 3 on the right? Does anyone have any guesses? On the right. Because what happens if I put it over here on the left? All of a sudden, I'm now saying there are 9 hydrogens. So that's what tells me I will be putting 3 on the right in front of the hydrogen. And in doing so, I've now balanced the hydrogens. I now say there are 3 hydrogens. What else have I done unintentionally? I've changed the number of chlorines. It's no longer just 1 chlorine. There's a big 3 in front of it. Now I'm saying there are 3 chlorines. So the idea of balancing is that it's a continual work in process. As you try to balance one thing, don't be surprised if you otherwise change other things. With that, I can say that in terms of hydrogen, we are now balanced. So a quick check is used to visually mark that for us. Continuing our discussion from left to right, hydrogen is fine. Next up is PO4. There's only 1 PO4 on the left. There's 1 on the right. It is already balanced. So just a quick check. Now on to sodium. There is currently 1 sodium on the left and 3 sodiums on the right. Right? This is what tells us this needs to be balanced. To balance it, we're just going to put a 3 in front of the NaCl. In so doing, we have now changed the number of sodiums. What else have we changed? The number of chlorines. Now on the left, there are 3 chlorines. We're not at the chlorine yet. We've confirmed the sodium is balanced. Now onto the chlorine, we see that there are currently 3 chlorines on the left. And well, would you look at that? There are already 3 chlorines on the right. Remember, we unintentionally changed the chlorines when we did hydrogen, but now we see that in our process of balancing, by the time we get to the end, everything is balanced. And this happens way more often than you think. That's why ultimately it doesn't matter which atom you start with, because by the end of it, everything should be balanced. Do we have any questions on this one? Okay. This is how we balance equations. It's a consistent battle of numbering, counting, changing, and all that stuff. Like I said, over the course of your practice, most likely by the end of this semester, everyone here will be able to balance this stuff in their head. Remember, we're only really doing whole numbers. But in the beginning, as you get even on Wednesday's workshop, I recommend taking your sweet time in the beginning. Taking patience now will help you a lot later. And while we're on it, I want to point something out about balancing reactions. We're only going to use whole numbers only. There's nothing wrong with a fraction every now and again, but we don't really like to use fractions if we can help it. Okay. That's how to balance reactions. It's something we'll never shy away from. So just a couple of practice out of the way is good because we'll be coming back to it again and again. Next up is the concept of state symbols and solubility rules. Now, state symbols are quite literally what they sound like. They are symbols that represent the state of matter. We know a couple of them so far. We know that solids exist. That's a state. And the state symbol for solid is just an S in brackets. S for solid. Similarly, another state of matter is liquid, which is given the symbol L. We also have the gaseous state, which should come as no surprise as being just a classic G. These are states of matter that we already know and are accustomed to, but now we're introducing symbols. When something is a solid, we call it a solid, we write S. When something is a liquid, we write L. When something is a gas, we write G. But now there is a new state symbol that we are introducing. It's known as the term aqueous. AQUEOUS. Aqueous is given the symbol AQ. Not just A, but AQ. Now, to understand what aqueous means, we have to recognize and know that most reactions, and when I say most, I'm talking over 90%. So let's go even further. Over 95% of reactions, most reactions, take place in water. What exactly does that mean? It means that you have test tubes and beakers that are filled with some amount of water. Within that water, you will have your chemicals that will be dissolved. And it's the water that acts as the medium. It acts as the place where the reaction takes place. In Chem 1A, pretty much every reaction we encounter will take place in water. So the term aqueous loosely describes how easy it is for molecules to dissolve. In other words, if a chemical is dissolvable in water, it is given the state aqueous. An example of this, table salt, sodium chloride. Although table salt is itself these small solid particles, table salt is dissolvable in water and is hence given the symbol AQ. This is written to the subscript, so the bottom right corner. Compare this to something like magnesium, and I'm talking a strip of magnesium metal. A strip of magnesium metal would not dissolve in water, so it is simply given solid. When it comes to the liquid, the only liquid we encounter is water. Because, of course, water cannot be dissolved in water. It's actually the only one that's given the L state symbol. It's very, very rare to see an L state symbol for others because, again, it's all about dissolving. Water is the only liquid you will see that has that state symbol, in 1A at least. The question then comes up, well, what about gases? How do we know which are gases How do we identify a gas? Well, from the periodic table, we know there are noble gases, right? Halogens are gases. What else do we know are gases? We know that diatomic elements are gases. We went over this when we talked about atoms and molecules. Examples of diatomic elements include hydrogen, fluorine, oxygen, nitrogen, and so forth. How else would you know that something is a gas? Information would have to be provided. What do I mean by that? I would have to say somewhere in the question, the following reaction results in a gas. Then it would be up to you to identify, make an educated guess as to which one is the gas. So liquids and gases are fairly straightforward to identify. Like I said, the only liquid we will encounter is water. And the gases are a matter of either you remember your diatomics or some information would be present in the question that would tell you a gas is present. So going back to our solid, how are we to know when something is dissolvable or not? Meaning, how do we decide if something is solid versus aqueous? This gives rise to the concept of solubility and its rules. That is this handout right here. This table dictates solubility, how to identify it, how to read it, and when things are not aqueous. Yes, Sarah. I'll put it this way. If this table tells you something is aqueous, it's aqueous. Otherwise, I would have to give you the information. So this table is how we identify if something's aqueous or not. So I'd like to take a few moments just to teach you how to read this. Now you all have the paper in front of you, of course, but I also have it on the TV. The column headings are meant to be read like a sentence, meaning if a compound contains a chlorine, then it is soluble, except when bonded to one of these guys. So it's meant to be read like a sentence. And hopefully you'll recognize that a lot of these ions seen here are ions from the polyatomic ions table. So there's a lot of overlap here. But I would like to read this using one of the reactions we've already covered. Let's take that first copper reaction. I'm going to write it on the bottom. Copper sulfide plus 2HCl gives us copper chloride plus dihydrogen sulfide. All right. So I know that part of the text is blocked by that meeting is recorded. Don't worry, I'll zoom in when we're there. Working from left to right, we're going to look at copper sulfide first. So we're going to go if the compound contains, and we're going to look through that list for either copper or sulfur. Pretty quickly, you should recognize, well, there is no copper in this at all, not in that table. However, there is a sulfur right down here at the bottom. So if the compound contains a sulfide, which it does, then it is insoluble, aka solid. There are exceptions. The sulfur would be aqueous if it's bonded to one of these ions. We have strontium, barium, calcium, NH4, and a group 1 cation. Copper does not meet any of those expectations, so this is not an exception. Therefore, the compound contains a sulfur, therefore it is solid. We would write that bracketed S. And it's written that superscript, that subscript, the small letter. This is how you would be able to tell if something is solid and will not dissolve, or solid and dissolvable, aka determine if something is solid or aqueous. Remember that only water, H2O, will ever be liquid. And gases is either dependent on your all preordained knowledge, such as diatomic elements, or some information present in the reaction. Let's keep it going. Next up, we have HCl. That is both H plus and Cl minus. All right. Looking at the first column, if the compound contains so technically hydrogen is a group 1 cation. So you could use that logic. If the compound contains a group 1 cation, which it does, then it is soluble, no exceptions. So I don't even need to look any further. It has a hydrogen. Hydrogen's a group 1. It's soluble, no exceptions. HCl is aqueous. Now, what if you didn't notice the hydrogen first? That's okay. If you looked for the chlorine would actually be the second one. If the compound contains a chlorine, then it is soluble, aka aqueous. Is hydrogen an exception? No. So aqueous. So two ways you could have identified AQ there. You either could have gone via the hydrogen first or the chlorine. Next up, we have copper chloride. So copper isn't on that list, so we're not going to look for copper, but we are going to look for chlorine. If the compound contains a chlorine, then it is soluble. Is copper an exception? No. So copper chloride is predicted to be aqueous. Lastly, we have H2S. Let me zoom in so we all can see. We have H2S, that's hydrogen and sulfur. Two ways to look at it. We can either go off of the group 1 cation or the sulfur. In principle, they should lead us to the same answer. Let's confirm. If the compound contains a group 1 cation, which it does, hydrogen, then it is soluble with no exceptions. So H2S is predicted to be aqueous. If you instead did it based off of the sulfur, sulfur is predicted to be solid, except when bonded to a group 1 cation. Hydrogen is in group 1. So in both cases, the H2S is predicted to be aqueous. We're going to try another example shortly, but does anyone have any questions on this? Yes, Joel.
Is it in order? This.
Not in one compound, right? You just mean like, what if you were evaluating these three ions separately? In theory, there should never be a case where they contradict each other, in theory. But based off of this one you just gave, Joel, so we're clear, this is not a real compound, this one right here. So we would not be able to consider it at all. But just to answer your question overall, in theory, they shouldn't, no matter what, lead you to the same answer, regardless of the order that you pick. As we saw with HCl, if you did it with hydrogen, group 1 cation, soluble, no exceptions. Great. If you did it in terms of chlorine, chlorine is also soluble and hydrogen is not an exception. So both perspectives should lead you to the same logic. And I think that should be true in every single case. Elena, what's up? So because of the weird nature of that, I would not give you mercury on an exam, but just so you know, mercury is liquid. It's what's in the thermometer, the red liquid in thermometers. That's why I wouldn't give it to you. It's a little bit ambiguous because sometimes it's a gas, sometimes it's a liquid, just depending on the environment. Yeah, good question. Or I would specify in the question, in this case, mercury is a liquid or whatever. I would not ask you to figure it out yourself. Good question. Any other questions on this? Yes, Prob. Yes. You mean the aqueous right here? Yeah. So two perspectives. We can either look at it from the H plus or the S2 minus. Let's look at it from H plus. Hydrogen is in group 1. And if the compound contains a group 1 cation, then it is soluble, no exceptions. So based on hydrogen, it's aqueous. If you looked at the sulfur instead, if the compound contains a sulfur, so right down there, it is predicted to be solid, except when bonded to a group 1 cation. Let me zoom in because I see that a little difficult to see. Hydrogen is a group 1 cation. So both logic, whether you go from the perspective of the hydrogen or the sulfur, you should reach the same conclusion, which is aqueous. Does that help? Great. Anyone else? All right. I would now like to do the next reaction we did. Let me just copy it right here. Paste. All right. How about you guys take a second to try to identify the state symbols yourselves for this the most recent reaction, the H3PO4. Take about 2 minutes to try that, 2 or 3 minutes, and then I'll go through the answers myself. Remember, as you go through the solubility checklist, it doesn't matter which ion you pick, the cation or the anion. They both should lead you to the same answer. Take another minute. This is a good example of you don't need to memorize this sheet. Like I said, it will be this table will be given to you on the exam. You do need to know how to use it and read it though. Okay, let's try it. Starting with H3PO4, regardless of the perspective you took, whether it be group 1 cation or the phosphate, you should have gotten this to be aqueous. Hydrogen is a group 1 cation, that's soluble, no exceptions. PO4 is traditionally solid, except when bonded to a group 1 cation. So again, it doesn't matter the perspective you take. Sodium chloride, sodium is in group 1. Group 1 cations are soluble, no exceptions, aqueous. Na3PO4, again, we have sodium. Sodium is a group 1 cation, no matter what, it's aqueous. HCl, without even looking at the chlorine, hydrogen is a group 1 cation. So this is, again, expected to be aqueous. The fact that all chemicals involved are aqueous doesn't really mean anything. There's no physical significance. It just so happens to be that they're all aqueous. Before I move on, does anyone have any last minute questions? Okay. Now we're going to talk about the different types of reactions. Let's make sure we're on. Yep. Reaction archetypes is up next. Yeah. And under reaction archetypes, we'll also learn how to predict products. Meaning, depending on the type of reaction, we'll predict products. The first one we will encounter is known as combustion. Within combustion, compounds of the form CXHY, these are sometimes colloquially referred to as hydrocarbons, will react with oxygen, aka burning, and always form CO2 plus H2O. So within combustion, hydrocarbons of the form CXHY will react with oxygen. It's called combustion, so it's really burning, and will always form carbon dioxide and water. This is the basic idea behind the burning of fossil fuels. Let's take an example of what this will look like. Take, for example, CH4, which is aqueous, will react with oxygen to give us carbon dioxide and water. Oxygen is one of our diatomic elements, so we should recognize that pretty quickly as a gas. H2O is water, which we should quickly recognize as liquid, so L. And then finally, we have carbon dioxide. Now, hopefully, most of us already know that carbon dioxide is a gas. CH4, you don't necessarily need to know this, of course, but CH4 is actually methane. It is a hydrocarbon of the form CH, where there is only one carbon and there's 4 hydrogens. That's all that's needed to be a hydrocarbon. There needs to be a hydrogen and a carbon. I see a hand, Sarah. It's not balanced yet. I know. That's part of what we're doing here today. Now, the products for the combustion will always be the same. They will always be carbon dioxide and water. It's really not much of a prediction. You know it for a fact. So the challenge here is balancing. Recognize that this reaction is not balanced. How can we tell that very quickly? There are 4 hydrogens on the left. There's only 2 hydrogens on the right. There are 2 oxygens on the left, and there are in total 3 oxygens on the right. So no matter what perspective you take, this is not balanced. We're going to work in order from left to right. There is 1 carbon balanced. That's fine. There are 4 hydrogens here on the left, but only 2 on the right. No big deal. We're just going to put a 2 in front of the H2O. In doing so, we have now balanced our hydrogens. 4 on the left, 4 on the right. What we have, I wouldn't say messed up, but what we have changed is the number of oxygens. Now, there are 2 oxygens on the left, and there are in total 4 oxygens on the right. In total, there is 2 from the CO2 and there is 2 from the H2O for a total of 4. To balance this, we're just going to put a 2 in front of the O2. Everything is now balanced. 1 carbon, 4 hydrogens, 4 oxygens, and in total 4 oxygens. So this right here is the completely balanced equation for the combustion of CH4. Since the products are very easy to predict, they're always the same, it's the balancing that is challenging for most people. Taking another example, C3H8, which is aqueous. In the presence of oxygen, again, will always form CO2 gas and H2O liquid. I'm now going to balance this, but first, I'm actually going to balance it in a specific order. I'm actually going to try to balance the oxygen first. When I try to balance the oxygen first, I recognize, well, there are 2 oxygens on the left, and currently there are 3 oxygens on the right. This isn't a very nice, easy, intuitive number because it's not like it would be 4, because if it were 4, we just put a 2 in front of it. If it were 6, we'd put a 3 in front of it and so forth. This is 2 and 3. You could, in theory, write 3 over 2, but that's a fraction. We don't really like working with fractions. So the point I'm trying to make here is that oxygen, although you could start with it first, it's a bit more complicated to start with it first. Remember, we talked about how by the end of the balancing, everything should work out. Well, occasionally there is a bad one to start with. In this case, in the case of combustion, do not start with oxygen. Let's start with everything else, though, and see what happens. From left to right, let's start with the carbon. There are 3 carbons on the left. There's only 1 on the right. That's no issue. Just put a 3 on the right. With that, carbon is now balanced. Next up, we have hydrogen. There are 8 hydrogens on the left. There are currently 2 hydrogens on the right. No problem there, though. Just put a 4 in front of the H2O. Now we come back to that very tricky oxygen, but let's take a look at what we have now. We still only have 2 on the left, nothing changed there. But on the right, we have 3 times 2, 6, 4 times 1, 4, for a total of 10. This is now a lot easier to balance because to get it to 10, all we need to do is put a 5 in front of the O2. So the point I'm trying to make here is that while ultimately you can pick whichever atom you want to start with, there are going to be some that are much more challenging than others. In those cases, I recommend you leave it to the end because as you can see, more often than not, it works out. I would like everyone to try this one on their own right now. C2H6 added to O2. And we, of course, know the products are CO2 and H2O. Take a couple minutes to balance it, and then I'll go through the answer with the class in just a bit. Take another minute. All right, this one is a little challenging. But we're going to trust the process. We're going to trust our efforts. We're going to keep it going. First up, we have carbon. From starting from left to right. There are 2 carbons on the left. No biggie. Just put 2 on the right. Carbons are now balanced. Then we have hydrogens. There are currently 6 on the left, 2 on the right. No biggie there. Just put a 3 in front. With that, we've balanced our carbons and our hydrogens. And all that's, of course, left is our oxygens. On the left, we currently have 2 oxygens. And on the right, we have that awkward 7. Let me use on top. 4 plus 3 equals 7. So that's an awkward number because yet again, we have a situation where it doesn't have a nice 2 times 4 is 7. 2 times 4 is not 7. You'd have to use a fraction. So that's a little uncomfortable because by all intents and purposes, we did everything correctly. It should work out, but we're not getting what we expect. That's okay though, because here's what we're going to do. If everything we tried on first doesn't work, assuming there was 1 in front of the C2H6, what we're going to do is we're actually going to bump it up. We're going to change it out. We're going to erase our numbers and then say, well, if 1 C2H6 doesn't work, let me purposefully put 2 in front of it. Why 2? Why not 3? Well, we're just going to go in order. We assumed 1 at first and balanced concomitantly. But this time, that 1 didn't really help. So we're just bumping it up to 2. Now, so we're going to try it again. Now there's 4 carbons on the left. We put 4 on the right. Now there are 12 hydrogens on the left. Let's put a 6 in front of the H2O. In so doing, now we have 8 plus 6 oxygens for a total of 14 on the right. That's a lot easier to deal with. So we're just going to put a 7 in front of the O2. So sometimes you can do everything right and it still doesn't quite work. What you do in that case is you just bump up one of your other compounds and see if that helps. Because balancing is just about the same idea if you've ever seen an accountant balance their checkbooks. You just want the numbers to work out. You want them to be similar on both sides. So whatever math magic you need to do to get it there, bumping up by 1, still works. Does anyone have any questions on combustion? Okay. On the other side of your handout, as I had mentioned, this was not a sheet for you to memorize or not that I'm going to give you, but just rather a summary. You can see under reaction type, the third one, this kind of goes over what I just talked about with combustion. It gives you a couple examples of what the reaction will look like. And it gives you a description that CXHY will react with O2 to form CO2 and H2O. So again, this page is just a summary of all of the reactions we're going to see, as well as some examples. All right. So that's combustion. Next up, synthesis. Synthesis is the most straightforward one. It's the idea of 2 or more chemicals combining into one. This one takes on the generic form. Oops, I don't want the yellow. A plus X gives us AX. And this is the generic reaction template. 2 or more chemicals combine into one. A and X combine into simply AX. Examples of this include such as sodium and chlorine. Sodium is a solid. Chlorine, as a diatomic element, is a gas. We can see that together, they come together and they form sodium chloride. Here's a question. Where did the 2 disappear to? Why did I not write NaCl2? Does anyone have any guesses? I see a hand right here. The charges cancel each other out. Sodium is +1, chlorine is negative. The face values are the same, so crisscross is just 1 to 1. So is it a problem that there isn't a 2 right there? No, it isn't a problem. It's just a reflection of the crisscross. So what do we need to do as chemists to fix this reaction? We need to balance it. Because of course, while we know that sodium chloride is aqueous, as written, there are 2 chlorines on the left, but only 1 on the right. So to balance it, we'll just put a 2 in front of the NaCl. That balances the chlorine. But what does it unintentionally do? It messes up the sodium. See, before I wrote the 2, sodium was fine. 1 sodium on the left, 1 sodium on the right. Chlorine was the one that's wrong. Now that I've balanced the chlorine is now right, but the sodium is wrong. No big deal though. I just fixed that by putting 2 in front of the sodium as well. Everything is balanced. The charges make sense. Everything comes together. Another example of this is a combination of H2 gas and Cl2 gas. Both diatomic elements, hydrogen and chlorine, so they're both gases. The result is HCl. HCl, according to solubility rules, is aqueous. Hydrogen is group 1 cation, so no exceptions. It's not that I'm wrong, but remember the 2's, those subscripts represent crisscross. In the case of hydrogen and chlorine, the crisscross is just 1 to 1. So all that's left, of course, is just to put a 2 in front of the HCl. That's synthesis. 2 or more chemicals combining into 1. Next up, decomposition. You might see some resources online or in your textbook refer to this as decay. Decay/decomposition, they mean the same thing. Well, quite literally, decomposition decay can be thought of as the opposite to synthesis. Where a single compound breaks, a simple compound breaks into its pieces or into its individual pieces, into individual chemicals. It takes on the generic form AX, breaks down into A plus X. So the literal opposite of synthesis. We saw these already. Sodium chloride breaks down into sodium and chlorine gas. To balance it, we'll put a 2 in front of the sodium and the sodium chloride. Where HCl breaks down into H2 gas and chlorine gas. To balance it, put a 2 in front of the HCl. That's decomposition/decay. All right. The next one, the last one we'll cover for today with the time that we have left, is known as double displacement. In double displacement, as loosely as I can best describe it, chemical compounds swap partners. The best way to describe this is just by use of that reaction. It takes on the generic form AB plus CD, here representing chemical compounds. We have here the A and the B. Remember, from left to right, we know that traditionally the left is the cation, the right is the anion. So in a chemical compound AB, we know that it's comprised of A plus and B minus. Same thing for CD. These are 2 different ions. So chemical compounds already, they're going to end up swapping partners, resulting in AD plus CB. So A goes over with D, C goes over with B. Now notice that in this output on this product side, AD, well, that's in alphabetical order. But CB is not, meaning I did not write BC. I wrote CB. Think about why that is. Remember that cations are written first and then anions. We know from this side over here that the C was always positive and that the B was always negative. So we write the cation first. So if you happen to write BC on an exam, you won't get it wrong. I'm just going to write a frowny face on beside it. It's not wrong. It'll just look really weird. I mean, instead of writing sodium chloride, imagine if you wrote chlorine sodium. It just looks weird. Let's take an example of what this double displacement means. Let us react sodium chloride with lithium fluoride. If you go by your solubility rules, both sodium chloride and lithium fluoride are aqueous. And the way how I've written it has already sort of nicely linked up the A's and the B's and the C's and the D's. So we know what's what. Now we're just going to swap them. We know on the product side, we're going to end up with sodium and fluorine. How do we know that? Because we know that A and D end up together. NaF. And then we have lithium and chlorine together. Again, how do we know they link up? Because C and B come together. NaF, group 1 cation, so both of these products are aqueous. And based off of balancing 1 sodium, 1 sodium, 1 chlorine, 1 chlorine, 1 lithium, 1 lithium, 1 fluorine, 1 fluorine. So in the case of double displacement, predicting products comes back to you recognizing they'll be swapping. How do you know that it'll be double displacement? Because there are 2 pairs of compounds. You can closely relate A, B, C, and D, and you can swap them. We're going to end lecture for here for today. Next time when we pick up on Wednesday, we're going to jump right into single displacements. And we're going to talk a little bit more about what to happen when we need to balance, crisscross, and all that nice stuff. We do have a wet lab at 1:30. That's about 17 minutes away. I'll see you guys in room 604 by then. If you have any questions, come talk to me now. If not, I'll see you in a couple minutes.
Unfortunately, we don't have any lab based on the schedule for the semester. If it's a future lab, you know, we can do that. So you can help you with the assignment. The ones that have already passed. Yeah, don't wear. Okay, don't wear. Okay, that makes.
Okay.